So, what do we have? We have half adders like this. In our incrementer, we have half adders. And right now we have put a 1 here. Okay. See, because we are insisting that it has to be tied to 1, you will recognize that this guy we may not be able to test some faults, because we can put a 1 here, that will allow 1 1 to be put on this input. We can put a 0 here and that will take care of 0 1, but we will never be able to put 1 0. Okay. So, there will be some coverage loss. Okay. So, by tying a cell to 1, we will lose some coverage, right. Such a design where the same unit repeats again and again is known as an iterative array. So, we can try and see, let me go to the next. So, we have an iterative array. For a minute, let us pretend that this output is not connected to 1. Okay, let us pretend that. See, suppose I apply uh, 0 1 0, okay, and I apply 0 here. So, this 0 plus 0 will result in a 0 here and a 0 here, and 0 plus 1 will return in a 0 here, I am sorry, a 1 here and a 0 here. Okay. So, effectively what has happened is, on these guys I was able to apply 0 0 and I am applying 1 0 0 0. Now, let me invert everything. So, I will apply 1 0 1. So, this time I am able to apply 1 0 here. So, I 1 0 and that will result in 1 as the output and the carry is still 0. So, this time I got a 0 0 here and that resulted in a no carry. So, 0 1. So, you can see that in the second vector this guy got 0 0, this guy got 1 0. So, if you look at every in every cell, okay, this is a half adder cell, we have to apply 0 0 1 0. Okay. Now, let us try whether we can apply 1 1. Okay. So, suppose I apply 1 1 1 and then 1 here. then you will see that 1 plus 1 will give you 0 as a sum, it will produce a 1 as a carry, 1 plus 1 is 0, carry 1 and so on. So, I have been able to apply all the 1 1. So, every cell has been tested with 1 1. Okay. Now, what remains is 0 1. Okay. So, we have to apply, is that possible to, let us try. Is it possible to apply 0 1 to all of them? Let me see. If I apply, I have applied 0 0. I am not very sure whether we can do that. So, what have we done? We have applied we have applied 0 zeros, I am sorry, I think we started with 0 1 0, then we applied 1 0 1, right, and then we applied 1 1 1. So, this is 7. So, that, and I think I have applying 1 here. So, I applied 0 1 0 plus 0, okay, and that caused 0 0 here, 0 1 here and 0 0 here. So, alternately I get 0 0 0 1 0 0 like that. When I apply 1 0 1 plus 0, initially I got 1 0 here, 0 0 here and I think this is wrong now. Did I do it right? When I applied 1 0 1 and I added 0, I think that is correct. Yeah, I think that was right. I have applied 1 0 1. So, the first cell will get 1 0, the second cell will get 0 0, the third cell get 1 0 and so on. So, we have managed to get 0 0 1 0. This should be 1 0. The last one was 1 1 1 and 1, that resulted in a carry of 1 and a carry of 1. So, 3 of the 4 I have been able to apply. So, 0 0 1 0 and 1 1. But are these sufficient? Okay. In our original circuit, will 0 0, what tests will it catch? Okay. When I apply 0 0, I get a 0 here and a 0 here. Under what conditions will the output change to 1? See, there is no way this 0 can change to 1, okay, with a single stuck at fault, but this will change. Okay. So, B1 1 will be caught, A2 1 will be caught, B2 1 will be caught, and B1 will be caught, right, and A1 will also be caught. So, these will be caught by 0 0. So, maybe this is also okay, right. So, earlier I had said that we will use 1 1, 1 0 and 0 1, and I had shown that all the faults are caught by these 3 vectors. If we can do it this way, then we can apply these 3 vectors 0 0, 1 0 and 1 1, and they also will catch all the faults. Okay. So, I am suspecting that 0 0 is also a valid, so this is a valid vector 0 0, 1 0 and 1 1. So, these 3, check if these catch all single stuck at faults in a half adder. So, I suspect that that is true, right. It will possibly, I think it will catch all of them, right. So, now the iterative array, we can easily test it with only 3 vectors. Okay. It is a constant number of vectors. So, this is a very interesting thing. In fact, we only applied 3 vectors. Okay. What are they? All ones added to 1, alternate zeros and ones adding 0, alternate ones and zeros adding 1. Okay. So, this I do not think was required. Okay. So, let me show you one more example in case this was not clear. So, suppose I have a 4-bit incrementer. So, my the test vectors that I have to apply are alternate zeros and ones, and here we have to add 0. So, this will produce a I am sorry, here we have to produce a 1. So, this will produce a 0, this will produce a no wait, no, something went wrong here, go back 0 1 0 1, right. So, we said 0 1 0 1 and we are adding a 0. So, this will produce 0, this will produce 0 and 0. So, you can say that for this half adder we have applied 0 0, we have applied 0 0, for this guy I have applied 1 0, for this guy I have applied 1 0. Now, I will reverse everything, I will say 1 0 1 0 and I again apply 0. So, this will give a 0 as carry, this will give 0 as carry, this will give 0 as carry. So, now 0 0 1 0 has been applied here, 0 0 1 0 has been applied here, 1 0 0 0 has been applied here, 1 0 0 0. Okay. Last is 1 1 and this time I apply a 1 here. So, that will end up putting a 1 everywhere. Okay. So, for each of the half adders, all the 3 have been applied. Okay. So, with 3 vectors, we can test all structural faults. So, what are the vectors? In the case of the 4-bit half adder, we are applying 0 1 0 1, that is 5. So, we are checking whether 5 plus 0 is equal to 5. The other one is 1 0 1 0, that is 10 plus 0 equals 10. And the last one is 1 1 1 1, that is 15 plus 1 is it equal to 0. Okay. In the modulo sum, this becomes 0, right. So, these 3 tests we did, okay. And interestingly it catches all the stuck at faults. Okay. So, such circuits are called C testable. So, what is C testable? Constant number of vectors. Are enough to test the circuit. Okay. So, this is a sort of interesting result, right. See, if I give you a counter, I am sorry, an incrementer and say test this incrementer, if you did not know this method, you may end up applying all kinds of tests, whether 7 plus 8 equal to 15, they may not be necessary. Okay. We have to take advantage of the regularity, okay, in the circuit. It is a very regular circuit, that is an advantage. So, this is what is called as an iterative array. We come across iterative arrays in many cases. For example, if you have a ripple carry adder, see, that is also a sort of a iterative array. We take a full adder, input carry x0 y0, then full adder x1 y1 sum 1 and so on. So, this is a very nice iterative array. So, if we know that internally it is built like this, what we are saying is we have a full adder with 3 inputs. So, if we can apply all the necessary inputs, so there are 8 inputs 0 0 0 0 0 1 and 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Among them some may not be required. Okay. So, we have to go and look at the internal structure of the full adder and argue which of these test vectors are really required for us to test. Then go back here and find x pairs of x and y such that all the full adders get the necessary vectors. Okay. So, I will leave that as an exercise for you. Okay. What is the exercise? Just like we analyzed the half adder, analyze the full adder and find the minimum number of vectors required to catch all single stuck faults. Okay, that is step number 1. Then in the step number 2, I want you to analyze a ripple carry adder. And the beauty is it does not have to be a 3-bit or a 4-bit or a 5. It can be as big a ripple carry adder that as you wish. Okay. Analyze the ripple carry adder and provide the xy values which will ensure that each full adder has been exercised with all the vectors found in step 1. Okay. So, step 1 is try to see whether we really do not need all the 8 vectors. You can argue and try to reduce that, and then take advantage of these smaller set of vectors and see whether you can find and that will give you a C testable. See, this is also C testable. A constant number of vectors will be sufficient to exercise all the full adders. Okay. So, if you did not design in an iterative way, right. So, there is an advantage in making an iterative array, right. In VLSI, okay, we like circuits which are iterative. That means we design it once, okay, and then duplicate that same thing. Okay. That is a very good design practice. Okay. It allows you to reuse the same module, okay, and in testing you may be able to apply iterative you may be able to take advantage of the iterative nature of the circuit and test it in a fewest number of test vectors. Okay. And even from a layout perspective, it is good to duplicate the circuit, right. So, there are what are called as systolic arrays. Okay. Systolic arrays are also like that. Okay. They are very regular. Each we may have small processors, okay, which do things like multiplication and addition, right, and that processor is repeated many times. Okay. For example, this may be capable of doing it receives 3 numbers and it produces, let us say, x times y plus s. Okay, it is a multiplication. It multiplies x and y, adds to s. Okay. If I make this as a major element, then I may be able to do things like matrix vector multiplication and things like that. Okay. So, you can read about systolic arrays and you will realize that because they are so regular, testing them may be somewhat easier, right. We can use that same property. Okay. So, nowadays people we hear about hardware accelerators for artificial intelligence. Okay. So, people are using there are in any AI application I believe there is a lot of matrix vector multiplication. And there are many matrix multiplications. So, you can give it some thought on how these can be tested using very few test vectors. Okay. So, that is a think problem for you. Okay. So, going back, we had let us return back to the sequential testing problem, right.